Hey, welcome. You know, in the world of health research, there's this one tiny number that holds a ton of power. It can decide if a new drug gets approved or if a massive health program gets the green light. It's called the p-value. And today, we're going to pull back the curtain and see exactly what it is and how it helps us make these huge, life-changing decisions.
Just imagine this for a second. There's a brand new health program, and the goal is to save lives. A lot of time, a lot of money is being poured into it. But that brings up the big question, right? How do we really know if it's working? How can we be sure that the good results we're seeing are because of the program and not just, random luck?
So, to get our heads around this, we're going to follow the journey of a public health researcher. She's staring down this exact problem, and we're going to see how she uses one key statistical tool to make a call that could affect the health of an entire community. Okay, so let's head to Ghana. Our researcher is on the ground where a new education program has just been rolled out. The idea is to help pregnant women quit smoking. I mean, the stakes couldn't be higher. We're talking healthier moms, healthier babies. She's got her data, but now comes the hard part, proving that the program actually made the difference.
Now, here's a fundamental rule in science. You can't just walk in and assume your great idea works. You have to prove it. And to do that, you have to start from a place of skepticism. It's really the foundation of all scientific testing.
So our researcher is basically looking at two competing stories. On one hand, you've got her research hypothesis. This is what she hopes is true, that her program actually helps women quit smoking. But to prove that, she has to first defeat the other story, the skeptic's view. We call this the null hypothesis. The null is the ultimate party pooper. It says, nope, the program does nothing. Any changes you see are just random noise. The best way to think about this is like a courtroom drama. The null hypothesis, that claim of no effect, is the suspect, and it's presumed innocent. Our researcher's data? That's the evidence she presents to the jury. Her job is to be the prosecutor, to show that her evidence is so strong, so overwhelming, that the only logical verdict is to reject that initial assumption of innocence.
Right, so how does she actually weigh this evidence? How does she decide if it's strong enough? Well, she uses a special tool, and this tool basically measures one thing, surprise, and its name is the p-value.
Okay, let's get the textbook definition out of the way first. The p-value is the probability of seeing the results you got, or something even more dramatic, if that null hypothesis were actually true. It's a mouthful, I know. Basically, it calculates the odds that you'd see this kind of improvement just by pure chance, assuming the program did absolutely nothing.
But honestly, here's a much simpler way to think about it. Just picture the p-value as a surprisometer. It just answers one question. If the skeptic who says this program does nothing is right, how surprising are my results? A really low p-value means your results are super surprising. It's a crazy coincidence. And when something is that surprising, you start to think, maybe that skeptic was wrong after all.
All right, so our researcher in Ghana does all the math, and she gets this one single number back from her analysis, a p-value of 0.02. So what on earth does that little number actually tell us?
Let's unpack this. A p-value of 0.02 means there was only a 2% chance of seeing this big a drop in smoking rates if the program was totally useless. A 2% chance? That's really unlikely. It's a highly surprising result, and because it's so surprising, that skeptic's no-effect theory starts to look pretty shaky. So, our researcher makes the call. She rejects the null hypothesis.
And rejecting that no-effect idea, it's not just some academic thing you write in a paper. This is the moment. It's the turning point where a researcher can finally stand up and say, the evidence is in, and it suggests this program actually works.
But that begs the question, right? How low is low enough to be convincing? Well, in health research, there's a widely accepted line in the sand. That cutoff for being surprising enough is usually a p-value of less than 0.05. So if the chance of seeing a result by luck is less than 5%, we say the evidence is strong enough. So let's peek at her actual data. Look at this. In the group of women who went through the program, the smoking rate was just 10%. But in the other group, the control group, it was 20%. I mean, it was cut in half. That p-value of 0.02 tells us that this huge difference is very, very unlikely to be just a random fluke.
So this all boils down to a really simple rule of thumb. Our researcher's p-value was 0.02. That's less than the 0.05 cutoff, so her result gets the official stamp, statistically significant. That gives her the scientific green light to conclude that yes, the program worked. Now, if her p-value had been, say, 0.30, she wouldn't have enough evidence, and she couldn't make that claim.
And what's really cool is that this whole logic, it's not just for things like smoking rates. It works just as well when you're comparing averages. To see what I mean, let's just imagine a different study for a minute. This time, testing a new drug for lowering blood pressure.
So, if you look here, the patients on the new drug have an average blood pressure of 125, but the folks on the old standard drug, they're averaging 140. That looks pretty good. And just like with the smoking study, the researcher would calculate a p-value. If that p-value is less than 0.05, she can confidently say the new drug works significantly better. It's the exact same principle, just with averages instead of percentages.
Okay, this is where the rubber meets the road. Getting that statistical result is one thing, but the next step, turning that data into real, tangible action, that's what really matters.
This is what it's all about. A statistically significant result isn't the end of the story. It's the beginning. For our researcher in Ghana, that low p-value is the key to getting more funding, to expanding her program to help even more women. This is how new guidelines get written for doctors, how governments decide on health policies. It's this whole process that leads to better care and, yeah, to saving lives.
So, when you really boil it all down, the p-value is so much more than just some number in a spreadsheet. It's a bridge. It's what lets us go from a pile of messy, uncertain data to a confident decision. A decision that can genuinely improve the lives of an entire community. So, we've figured out how researchers use this p-value to spot a significant result. But here's a final thought to chew on. Just because something is statistically significant, does that automatically mean it's truly meaningful in the real world? That's a whole other can of worms and maybe a topic for another day. Thanks for joining me.